Hello and welcome to Engineer Simple. In this video, I'll be talking about capacitance in series and voltage divider. Capacitors are sometimes called condensers. So when you have a capacitor, so the current through the capacitor is equal to capacitance times the derivative of voltage with respect to time. So if we take a quick example, if we have a voltage across a capacitor, which is 100 times sine of 2 pi times the frequency times time through a 5 microfarad capacitance, then what is the current through this capacitor? So if we apply this equation here, so we know current is equal to C times the derivative of voltage with respect to time. Capacitance is just 5 microfarads or 0.1234505 times the derivative of sine 2 pi times f in this case is 60 times t with respect to time. When now the derivative of sine is just cosine, then you take the derivative of 2 pi times 60t, which is just 2 pi 60. So the derivative of sine is cosine, then the derivative of what's inside the sine, 2 pi times 60 times t, is just 2 pi times 60. So if you do the math, the current is equal to 0.001884 times the cosine of 377 times t. 377 is just 2 times pi times 60 amps. So if we know the current and we would like to calculate voltage, then we would have to perform integration. So voltage is equal to 1 over the capacitance times the integral of current. So where integration is from negative infinity to some time t. So one fact about capacitances, they store energy in electric fields. Resistors or resistances, they consume power or they dissipate, they consume power as heat basically. And inductors, they store energy in magnetic fields. So capacitors or capacitances store energy in electric fields. So that's a fact about capacitances. This energy is stored until it's returned to the circuit. So this energy is 1/2 times the capacitance times the voltage squared. Now, let's assume we have a bunch of capacitances in series. Like this graph here shows, you have source, it goes through capacitance 1, capacitance 2, dot, 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 to capacitance N. So all these capacitances are in series. So we know since this is a series circuit, so the voltage V is equal to the voltage drop V1 plus V2 plus dot 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 plus Vn. So that's what I'm writing here. And we know since it's in series or a series circuit, the same current flows through all these components. So from the previous slide, we know that the voltage across a capacitor is 1 over C times the integral of the current, where integration is from negative infinity to some time t. So if we do this for each capacitor, so basically in this formula here, just apply that to each capacitor. So it's 1 over C1 times the integral of the current. Since the same current flows through each component, then we'll just keep the same current, plus 1 over C2 times the integral of the current, plus dot dot dot, plus 1 over Cn times the integral of the current. As we notice here, the integral of the current is kind of common to all these terms. So we can factor that out. So that's what I'm doing here. So it's the integral of current times 1 over C1 plus 1 over C2 plus dot 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 plus 1 Cn equals. So what I'm doing here, this 1 over Cs basically is the equivalent capacitance of all the capacitances in series. It's just equal to this term here, the entire quantity. So 1 over Cs, so Cs is just the equivalent to capacitance of the capacitances connected in series, is equal to 1 over C1 plus 1 over C2 plus dot 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 plus 1 over Cn. In other words, if I want Cs is just 1 over the entire quantity. So if you notice here, capacitances in series are kind of like resistances in parallel. So in the previous slides, time domain was used, that is time, or t was used. So we had to do derivatives, we had to do integration. Typically, engineers do not like to deal with derivatives and integration. So it's a lot easier to do all the calculations in frequency domain, then you convert back to time domain if needed. So one way you can do this is using phasors. So if you see here, lowercase I basically just says it's time domain is equal to capacitance times the derivative of voltage with respect to time. So I replaced lowercase I, which kind of implies time domain, with I, uppercase I, which implies phasor or frequency domain, times C. C is a constant, is just a constant. Then so notice here, so the operator d divided by dt, I replace that with j times 2 pi times the frequency. So that's how we kind of don't have to deal with derivatives. Then the voltage in time domain is just uppercase V, which implies it's a phasor. So basically the conversion from time domain, from this here, time domain, to frequency domain, as you can see here, everything is with respect to time. Instead, I'm using frequency. Basically, I use this operator here and replace it with the term j times 2 pi f. So we can rearrange this. So this equation here is is current. If I want to find voltage, basically just kind of do some math. So voltage just negative J times the reactance of the capacitance times current, where basically I just took 1 over 2 pi f and just called it reactance of capacitance. So that's all I'm doing here. So rearranging, current is equal to J times 2 pi f times C, which is capacitance, times voltage. And if I replace 2 pi fc with the reactance, so it's just 1 over x of C times voltage. And I would recommend watching other videos where I showed that the operator J, so J basically it's just an imaginary term which is equal to the square root of -1. And if we write J in a polar form, it's just 1, magnitude 1 with an angle of 90. So basically That's what I'm doing here. So this is current. If I want voltage, just to kind of some rearrangement, so I get voltage equal to the reactance of the capacitor times the current. So this is just Ohm's law basically. So voltage equal to impedance or reactance or resistance times current with an angle of -90. So notice here current is 90, voltage is -90. This is for capacitors. So what this tells me here, voltage lags, or it's behind current by a 90-degree. So reactance of a capacitance is just 1 over 2 pi Fc. And you can go back here, we'll go back to this equation here to see how I came up with this term here. But if we assume this capacitor is a pure capacitor, that means there is no resistance. So the impedance of the capacitor is 1 over J times 2 pi Fc. And if you watch the previous videos, the impedance of an inductor is J times 2 pi times F times L. F is frequency, L is inductance. But for the capacitor, it's 1 over. And this has some impacts on power systems, which we'll see in later videos. When you have basically inductances and capacitors in circuit, they can cause some problems. One of them is resonance, but we'll talk about that at later videos. So it's important to understand these concepts, capacitance, inductance, resistance, like how they behave. Then once you understand them, it's really easy to analyze or design any system. So if we have a bunch of capacitances connected in series, so if we call them C1, C2, Cn, then in time domain, as we saw previously, the voltage is just the integral of the current times the equivalent capacitance, or 1 over the equivalent capacitance of all the capacitances in series. So that's in time domain. But time domain, you can see you are dealing with integration, and if you are doing current, you will be dealing with derivatives. And as I said, engineers typically they don't like to deal with integration and derivatives. So that's why phasors are a lot easier to deal with. So if I want to go from time domain to frequency domain, so lowercase v becomes v equal to -J times the reactance of each capacitor times the current. So if you do that for all the capacitances, and if you want to know where this negative sign came from, you can go back to the previous slide. And just as a reminder, the reactance of the capacitance is 1 over 2 pi times the frequency times the capacitance. Or if we want the impedance is 1 over J times 2 pi times the frequency times the capacitance. If I multiply both sides by J, so 1 times J is just J, J times J is -1, and so that's why you have this negative sign here. Because if you want to move J from the denominator to the numerator, that's what happens basically. You get a negative sign. So you can rewrite this equation here as voltage equal to -J times the sum of all reactances times the current. So in other words, really what I'm doing here is just Ohm's law, basically. So now voltage divider. So anytime we talk about circuits in series, we also talk about voltage divider. So if I want to know the voltage across capacitance 1, each capacitance, so let's take capacitance 1 for instance. V1 is equal to the reactance of capacitance 1 divided by the equivalent reactance, or the reactance of all the reactances in series times the source voltage, which is here. So X of S is just all the reactances in series summed up. So let's do a quick example. So in time domain, so if you have a signal of V is equal to 120 times sine of 377 times t, and again 377 is just 2 pi f, 2 pi times 60 hertz basically. In the United States it's 60 hertz. In other countries it might be 50. So if we assume we have a capacitance of 0.003 farads, then what is the current? So, and I'm going to do this instead of time domain, I'm going to do it in frequency domain or phasors. Then I can show you how I can go from phasor to time domain. So I can write this here as magnitude, which is 120, and an angle. So 377t plus 0 basically. So that's why I put 0 here. Then, so we'll solve in phasor form. Then we'll convert to time domain. So now in this case, as you can see, I don't have to deal with integration, derivatives, or anything. So it's very slick. So we know the reactance of the capacitor is 1 over 2 pi times frequency times capacitance. So if I just plug in the numbers, I get 0.8842 ohms. So we know from the previous slides, the current through the capacitor is voltage divided by negative J times the reactance of the capacitor. In other words, all I'm doing here really is just Ohm's law. So V is 120 with an angle of 0, and the reactance of, or if I take this here, negative J times X of C is just 0.8842, so that's why I'm putting here. Negative J is just an angle of negative 90. And again, I would recommend going back to some of the videos where I talked about polar form and phasor operations to see how we go from like J or negative J to negative 90 or 90 degrees for J. So if I do the math, it's 135.7 with an angle of 90 degrees. Because if you see here, so when you have, and again, I would recommend going back to those videos. So the magnitudes, basically you take 120 divided by 0.8842 gives you 135.7. For the angles, when you have division, you take angle 0 minus 90. That's why we have plus 90. So again, from here, 1 over negative J is just 1 over a magnitude of 1 with an angle of negative 90, which is just 1. If you bring angle of 90 up, you change the sign basically. So how do I go from here to basically phasor notation or frequency domain to time domain? So then I just take the magnitude 135.7 times, I started with a sign right here, so I stick the sign here, and I have 377t, so I stick that here, then plus the angle of the phasor, which is 90. So that's why I put 90 here. And from trig equations, when you have sine of x plus 90 is just the cosine of x. So that's what I'm doing here. So now, so you can see solving this problem in frequency domain was easy because I didn't have to do integration or derivatives. So now let's solve in time domain only. So current is capacitance times the derivative of the voltage with respect to t time. So if you plug all the numbers, so then you know the derivative of sine is just cosine. The derivative of 377t is just 377. That's why I have it here. So if you plug all those numbers, you get 135.7 cosine 377 times t. This one was not that bad because I only had one term of sine. But when you have multiple sources, it's kind of pain. But anyway, this little exercise kind of shows how you can go from time domain to frequency domain, or frequency domain back to time domain. Those two concepts are important in circuit analysis. Thank you and have a great day.